Hello everyone, myself Sonia. Today my topic on thermodynamics from modern physical chemistry BSc part 2 by S. Kiran. Let's start. Thermodynamics Introduction. The most common form in which energy appears is heat. Thermodynamics is a theoretical method which can be applied to the process involving absorption, evolution, or transfer of heat. The word thermodynamics means study of flow of heat because therm means heat and dynamics means movement. However, as we move further, it will be seen that the subject involves a more generally quantity, that is energy. Besides heat, there are many other forms in which energy appears, like mechanical energy involved in motion of mechanics, electrical energy exhibited by flow of electron in conductor, radiant energy in visible light and radiation in general, and finally chemical energy, the energy stored in all substances and which appear when substances undergo transformation. All these forms of energy may seem distinct but may be transformed into one another under certain conditions. A study of this interrelation of various forms of energy in a system constituent the subject of thermodynamics. Thermodynamics may be defined as the branch of science which deal with the quantitative relationship between heat and other form of energy. When we study energy changes accompanies the chemical process, it is referred to as chemical thermodynamics. Thermodynamics is primarily based upon three fundamental generalization called the first and second and third laws of thermodynamics. These laws have been arrived at purely on the basis of human experience. In addition to these laws, there is another generalization which was put forth at a later stage and is known as zeroth law of thermodynamics. Though there is no theoretical proof of these laws, the predication based upon these laws have been verified and no contradiction have been reported so far. In general, zeroth law provided the basis for the measurement of the temperature. First law deals with the equivalence of various forms of energy. Second law deals with the direction of given chemical process. Third law deals with evaluation of thermodynamics parameters like entropy. Number two, scope and objective of thermodynamics. The importance of thermodynamics lies in the fact that it provided explanation of macroscopic property, that is bulk property of matter in term of microscopic concept of matter. Thermodynamics deals with chemical energy, that is the study of energy changes during chemical reactions. The thermodynamics and chemical energy find application not only in chemistry but also in other branches of science like engineering and technology extra. Some of the way in which thermodynamics can be useful as follows. Number one, to predicate the spontaneity or feasibility of process. Thermodynamics help to predict whether a given physical or chemical process is feasible under the given set of conditions. Number two, to predict the extent of reaction. Thermodynamics can predict the extent upon which reaction can proceed before the equilibrium is attained. That is, it can help to determine the yield of chemical reaction. Number three, to reduce some important laws of physical chemistry. Some important law of physical chemistry such as Raoult law, Van Wolff law, distribution law, phase rule, etc. can be deduced from the law of thermodynamics. Limitation of thermodynamics. Number one, it studied the property of matter on the macroscopic scale. scale, that is the system involving very large number of molecules. The law of thermodynamics are not applicable to individual atoms, molecules or ions. So thermodynamics does not give an insight to structure of matter. Number 2, it gives the relationship between various experimentally observed properties, but it unable to give the actual value of these property. Also, it does not explain as the why these property arise in a system. Number 3, it can predict the flexibility of process, but does not give any information regarding the time taken for the process to complete and the rate at which the process take place. Number 4, it is concerned only with the initial and final state of the system. It failed to tell the path by which the process is carried out. Hence, it does not throw any light on the mechanism of the process. One some common thermodynamics term. Number first, system boundary and surrounding. A system is defined as the part of universe under investigation, separated from the rest, called the surrounding by real and imaginary boundaries in order to study the effect of variables such as temperature, pressure, volume, extra upon its contents. The remaining portion of the universe other than the system which may be capable of exchanging energy and matter with it is called its surrounding. So universe is equal to system plus surrounding. The system and surrounding or the separated by real or imaginary surface called boundary. The boundary defined the limits of a system. The system and surrounding exchange matter and energy through this boundary. Consider 1 mole of gas confined in a cylinder fitted with a piston. The gas constituent the system, the cylinder, piston, and everything outside the cylinder from the surrounding. Number 2, types of system. On the basis of exchange of matter and energy with the surrounding, there are three types of system. First, number A, open system. Second, closed system. Third, isolated system. First, open system. Hot tea is an open cup. Open cup is an example of open system. It can transfer heat as well as water vapor with the surrounding. In this type of system, the boundary is open, and therefore an open system is one which can exchange matter as well as energy with the surrounding. Water heated is an open beaker is an example of open system. It can exchange both matter and heat with surrounding. Similarly, a reaction between zinc and dilute hydrochloric acid taking place in an open beaker is another example of open system. The hydrogen gas involved evolved ex- escape into the surrounding, and the heat evolved during the reaction is transferred to the surrounding by radiation. Number 2, closed system. In this type of system, the boundary is sealed but not insulated. Therefore, a system which can exchange only energy in the form of heat, radiation, or work, but cannot exchange mass with the surrounding is called closed system. Hot is in a closed steel flask is an example of closed system. It can transfer heat through the walls of the steel flask of the to the surrounding, but no matter can escape from this system. A chemical reaction taking place in a cylinder fitted with a piston is an example of closed system. It can transfer heat through the walls of cylinder. However, no exchange of matter can take place with the surrounding. If the wall of cylinder are insulated and the reaction is accompanied by an increase in volume, then the piston move up and may work is done by the system on the surrounding. The energy in the form of mechanical energy has been transferred from the system to the surrounding, but there is no exchange of matter as the cylinder remain closed throughout. Number 3, isolated system. In such type of system, the boundary is sealed and insulated so that no exchange of matter or energy is possible with the surrounding. Therefore, a system in which neither the energy nor the matter can be exchanged with the surrounding is called isolated system. For example, a liquid is contact with its vapor is an isolated closed vessel is an isolated system as the vessel is closed, thus vapor or liquid cannot either leave or enter the vessel. There is no exchange of matter with the surrounding. Further, as the vessel is insulated, the system cannot exchange heat with the surrounding, hence it is an isolated system. However, perfectly isolated system does not exist. However, a system which is sealed and perfectly insulated from the surrounding in a close approximation of a isolated system, as it can neither lose or gain energy or matter to the surrounding. Number 3, homogeneous and heterogeneous system. Homogeneous system, when a system is completely uniform throughout it is called a homogeneous system. A homogeneous system has only one phase. For example, a pure solid, a pure liquid, a solution of two completely miscible liquid, a mixture of gases. All these systems have only one phase, so the system is uniform throughout, hence it is called it, homogeneous. Have only one phase, so the system is uniform throughout, hence it is said to be homogeneous. Heterogeneous system, if a system is not uniform throughout, it is called a heterogeneous system. In other words, a heterogeneous system consists of two or more phases which are separated by boundary. However, each phase is on in its own is uniform. Ice cups in a glass of water, a mixture of oil and water, a mixture of iron filling and the sand are few examples of heterogeneous system. Following are general example of heterogeneous system: a mixture of solid and vapor, a mixture of solid and liquid, a mixture of two or more solid, a mixture of two or more immiscible liquids. Macroscopic system, a system containing a large number of particles is called macroscopic system. Macroscopic property, the property of system isolated with the bulk behavior of the large number of particles in a macroscopic system is called macroscopic property or bulk property. These property are pressure, temperature, volume, composition, viscosity, density, etc. For example, in order to note the temperature of water, we do not deal with individual molecules, but we consider the molecule in bulk. So temperature is a macroscopic property. Macroscopic property can be divided into following two types: extensive property and intensive property. Property is the property of system which depend on the quantity of the matter present in the system, or called extensive properties. Some common example of these properties are mass, volume, internal energy, enthalpy, heat, capacity, etc. Intensive property, the property of the system which are independent of quantity of the matter present in the system, or are called intensive property. Temperature, pressure, refractive index, viscosity, specific heat density, extra some common intensive property. It may be denoted that extensive property are additive in nature, whereas intensive property are not. For example, consider water taken in beaker. If we double the volume of water, the mass is now also doubled. So mass and extensive property is additive in nature, whereas if we take water in at 25 degrees Celsius in a beaker and double its volume, the temperature of water will remain the same, that is 25 degrees Celsius. Therefore, temperature and intensive property is not additive. Further, an extensive property may become extensive property when it is specified for the until amount of the substance. For example, mass is an extensive property, but density, that is more mass per unit volume, is an intensive property. Similarly, heat capacity, which is an extensive property, but specific heat, which is the heat capacity per gram of the substance, is intensive property. Table